The Schema evolution system manages structural changes to stored objects across distributed instances. When a field definition is modified, added, or removed, the migration framework ensures backward and forward compatibility throughout the cluster. This document describes the version tagging mechanism, migration directives, and field resolution behavior during read and write operations on version data. The versioning system uses a major.minor.patch tuple stored within each data structure header. The major version increments when backward compatibility is broken. Minor increments indicate new fields or optional properties added to the schema. Patch increments reflect internal representation changes that do not affect external interface. Versions are immutable once assigned to a schema release. Migration directives are defined in the schema manifest as ordered transformation steps. Each directive specifies the source and target versions, the field affected, and the transformation operation to be applied. Operations include rename, type convert, split, merge, and drop. Directives are processed sequentially. The system maintains a migration dependency graph to detect cycles or conflicting transformations. During read operations on a record with a lower schema version than the current system version, the resolver applies all applicable migrations in order. The result is presented to the application in the current schema format. If a migration directive cannot be applied due to missing data or type incompatibility, a default value is substituted according to the field definition's null handling rules. Write operations perform the inverse process. When an application submits data matching the current schema, the writer examines the target record's version. If the target is at an older version, a migration path is computed to downgrade the outgoing data to a compatible intermediate version. This ensures older readers can still parse the data even if they cannot interpret all fields. The compatibility matrix defines which versions can directly interoperate. Two versions are compatible if there exists a series of unambiguous migrations connecting them. The compatibility matrix is computed during schema compilation and cached for runtime use. Queries can be restricted to a minimum version range to avoid expensive migration chains. Field metadata includes a deprecation timestamp and a sunset date. Deprecated fields are still parsed and written but are marked for eventual removal. Queries can filter on deprecation status to identify records containing deprecated fields. The sunset date triggers warnings in logs when exceeded. Active use of sunset fields is reported separately to administrators. Type conversions are applied using strict rules to prevent data loss. Numeric narrowing operations, such as converting int64 to int32, are allowed only if all existing values fit within the target range. String to numeric conversions require explicit format specifications. Boolean fields may be derived from nullchecks or presence markers when the source field does not directly represent a Boolean value. Field splitting occurs when a single source field must be divided into multiple target fields. The split directive includes a parsing specification, typically a regex pattern or format string. If parsing fails, both source and target fields receive default values, and a migration error counter is incremented. The error is logged but does not block the operation. Field merging combines multiple source fields into a single target field. The merge directive specifies a template string or a function name. Template strings use placeholder syntax to interpolate field values. Function-based merges are resolved by name at runtime. If the function is not available, merging fails safely and a default value is applied to the target field. The drop directive marks a field for removal and specifies a data retention policy. Immediate drop removes the field from the record. Lazy drop retains the field in storage but prevents new values from being written to it. Queries still see the field with existing values. Archive drop writes the field to a separate audit table before removal. Migration tracking uses a Bloom filter to identify records that have been migrated at least once. This optimization avoids recomputing migration paths for records already in the current version. The Bloom filter is rebuilt during compaction cycles. False positives cause unnecessary migration checks. False negatives cause data corruption and are detected during verification scans. Validation rules are defined per field and per version transition. A validation rule specifies constraints on field values, such as regex patterns, numeric ranges, or a non-membership. Validation occurs after migration. If validation fails, the record is quarantined and a validation error is reported. Quarantined records are excluded from normal queries until manually reviewed. The migration cost model estimates the computational overhead of a particular migration path. Each directive carries a cost weight based on operation type and field size. Queries can specify a maximum cost threshold. Paths exceeding the threshold are rejected and the query fails with a specific error code rather than performing the migration. Rollback operations are supported for in-progress migrations. A rollback directive specifies the target version to revert to. The system computes the inverse migration path by reversing the order of directives and applying their inverse transformations. Data loss is possible if fields have been dropped. Warnings enumerate affected records before rollback proceeds. Schema manifest files are stored with full history in the metadata repository. The manifest includes version tags, migration directives, validation rules, field metadata, and compatibility matrices. Compiling a new manifest against the existing history validates that no contradictory migrations are introduced. Invalid manifests are rejected before being published to the cluster.